Now, if you actually wanted to get a numerical result for this, since we do have numerical representation of our two distances from the center, I'll give you the numbers, okay? G is this and M is this. Earth has a mass of 6 times 10 to the 24 kilograms. I think it's actually 5.97, close enough to 6. And 6.67 here, and I don't remember what the other decimal places or the other figures are, times 10 to the negative 11 Newton meters squared per kilogram squared. The units and everything work out. You put them in here, put big M and big G in here, and put a distance R. And of course, this only applies if the distance is greater than the radius of the planet. It doesn't apply when you're inside the planet. If you're inside the planet, incidentally, you just get to use the mass that's closer to the center than you are. All the mass that's further from the center doesn't count anymore. Okay, in any case, you plug these numbers in here. Of course, your kilometers are going to have to articulate with the meters here, so you're going to probably change the kilometers to meters. And you're going to get the amount of energy and per unit of mass. And then if you choose a mass, you can, of course, find the energy. And that's what this expression would be, the change in the potential energy, the work you got to do against gravity to get up there. Okay, the other part, as I mentioned, this is not related to MGY. Okay, I mean, it's related in the sense that it's work done by gravity between a couple of points, but the two situations are completely different. Although this one would reduce to this one for very small changes in R near the 6,400 kilometer radius of the Earth. Okay, now another thing I'm going to say is we're only defining here the change in potential energy, and I've commented that this MGY, I don't like this because, well, for reasons that I've enumerated, mainly because people grab this and use it whether it applies or not. That's the thing I really don't like about it. Prefer to think in terms of changes in potential energy. But now that we have the change in potential energy between 2 points, let's just say, okay, we've only defined change in potential energy, but now that we've defined the change in potential energy, we can define potential energy relative to chosen position, where we say that potential energy is 0. We could, for example, take the chosen position to be the surface of the Earth. Now, that would work, but you would have to get an expression for the potential energy, which is a little more complicated than it needs to be. And I don't want to go into the details of that. I'm simply going to say the simplest place to call the potential, to say that the potential energy is 0 when you're dealing with this situation, where you're dealing with the universal gravitational constant and distances from the surface of the planet on out. The most convenient thing to do is to say, what is to notice that this expression approaches 0 as R approaches infinity. Okay? Now, we want to have the potential energy at our chosen position to be 0. It's therefore convenient to choose infinity as our chosen position. Although we can only approach infinity, we can't reach it. It's not really a position. But we measure our potential energy relative to our chosen position. We're going to measure the potential energy here relative to infinity. And since this expression itself approaches 0 as R approaches infinity, this is going to be our expression for the potential energy relative to infinity. Now you might want to start digesting that idea. It's going to be very important at later points in the course, although I'm only really trying here to militate against the idea of always using MGY. And that's the main reason for this digression. So this is not something you need to know now, but you should understand that MGY is not written in stone. It only applies near the Earth, and I really just prefer to think in terms of changes in potential energy.